The most common application of derivatives and antiderivatives by far is position, velocity, and acceleration, because that's the most common topic that we can talk about how fast something is changing. How fast your position changes is your velocity. So if you want to move down this little ladder, we take the derivative. And then how fast your velocity changes is your acceleration. Take a derivative again. All right, these are topics that we talk about on a day-to-day basis. If you want to go the other way, if you know acceleration and you want to know velocity, then it makes sense that we will take antiderivatives. And again, to get to position. Now there's more to it than that. We'll have the constants and initial positions and initial velocities and things like that. But in general, this most important application of calculus, this is the pattern: position, velocity, acceleration. So we're going to come back and talk about these topics now that we know how to integrate. We talked about them before when we knew how to differentiate, and now we're going to use integrals. So we're going to play a little Mythbusters and talk about two urban legends, I guess you could call them, that I believed or heard as a kid. So I heard as a kid that if you dropped a penny off the Empire State Building and it hit somebody in the head, it would bury through their skull and right into their head. And kind of sick, I know, but let's see how fast a penny would be going if we drop it off the top of the Empire State Building. So the things we know are how tall the building is, 1,454 feet. And we know here on Earth, gravity causes things to accelerate downward at negative 32 feet per second. And those of you that have studied some physics, a lot of this will look very familiar. One thing that needs to happen is we need to neglect air resistance, which always bothered me in physics, because where do you go where there's no air and stuff doesn't fall through an empty space, it falls through the air. So if you dropped a penny, in reality it would probably be kind of fluttering back and forth because it would catch some of the air. But in problems like this, we ignore it. We can just say that acceleration is negative 32. So let's build our functions. Remember, we need to anti-differentiate, starting with acceleration. So t is going to be our variable, time, and acceleration is a constant negative 32, and that's measured in feet per second squared. If you see or remember the number negative 9.8, that's if you're measuring in meters. But we'll do feet. So if acceleration is negative 32, then let's talk about velocity. Velocity is the antiderivative of acceleration. So it's negative 32t plus a constant. Now that constant, because of the nature of this function, if you let t equal 0, then this constant will equal the velocity. In other words, this constant is the initial velocity. So sometimes instead of writing it as c, we'll just write it as v with a little sub-zero, v naught, v sub-zero, and that's initial velocity. And one key fact here is that if you drop something, keyword in the question, drop, you just hold it out in your hand and let it go, then it's going to have an initial velocity of 0 because you didn't throw it, you just dropped it. So v of t equals negative 32t. So if we want to know the velocity of this penny at any moment, we just plug the t, how many seconds it's been traveling, into this equation. And then let's get our position function. The antiderivative of negative 32 is negative 32t squared over 2 plus, and now this constant, similarly, is the initial position, s sub 0. And for us, that's 1,454 feet. So the position of this penny at any moment is negative 16t squared, because I divided 32 by 2, plus 1,454. So we've got the acceleration that was given, we have the velocity in terms of t, and now we have the position in terms of t. And let's go back to the original question. How fast will this penny be moving when it hits the ground? So think about that. When it hits the ground, what is true? Well, its position when it hits the ground has become 0. So this just involves solving this equation. 0 equals negative 16t squared plus 1454. Okay, s of t is the position, or the height in this case. Right, we're doing one-dimensional motion along a line. In physics class, you'll do projectiles that travel, and you've got some x parts and some y parts. We're just doing something that, in this case, goes straight down. And we are mapping its position and its velocity over time. So what I know is the case is that my position is 0 when the penny hits the ground. And if I solve this equation by moving 16t squared to the other side, and then dividing by 16 and then square rooting, I'm going to get t equals 9.53 seconds. And I'll save that for you to check, but that's just 1454 divided by 16 and then square rooted. But remember the question. Actually, we did how long will it take to hit the ground? That is 9.53 seconds. And how fast, in other words, velocity. What is the velocity going to be at 9.53 seconds? Well, that is v of 9.53, which is simply negative 32 times 9.53, or negative 305, let's round it to negative 305, and that is in feet per second. So it's going to take almost 10 seconds to get to the ground, and it's going to be traveling at 305 feet per second. And just to get a reference point, because most of our speeds are in miles per hour, that's negative 208 miles per hour. So honestly, I still don't know whether that would go through your head or not, but we know how fast it's moving. All right, so this is a good application of position, velocity, acceleration. And notice that both of these are negative, because this penny is moving down. Up is positive, down is negative. All right, here's another one. I used to think, or I have heard, that if you want to know how fast you throw something, throw it up in the air, count the number of seconds that it takes to hit the ground. And if you can throw something that stays in the air for 6 seconds, then you threw it at 60. 7.5 seconds, you threw it 75, and so on. So multiply your seconds by 10, and that's the miles per hour. And before making this, I've never checked to see if this was true. I just want to check out a childhood urban legend to see if it's true or not. So let's do an example. Let's say Benny throws a ball from an initial height of 5 feet. So that's, his hand is not on the ground when he lets the ball go. So the initial height is 5 feet, and the initial velocity is 50 miles per hour. All right, because he's going to use a radar gun that they use to measure, baseball pitches. How long does it take the ball to hit the ground? So if it takes 5 seconds, that would show that this urban legend is true. So let's see. You throw something up from a height of 5 feet with a speed of 50. How long does it take to get back down to the ground? And we'll use a clean slide to answer that question. So the info that I know is that S sub 0 equals 5. That's initial position. S is the letter we use for position, and sub 0 means at time 0. You could also call it S of 0 equals 5. The initial velocity, I'll get rid of that, we'll just leave it at S sub 0, but the initial velocity equals 50. Okay, so if we want to use the given value of acceleration, which is negative 32 feet per second squared, usually when we throw things, especially baseball players, and we measure that in miles per hour. So let's get this initial velocity into the proper units. If 50 miles per hour, we need to multiply that, do a little unit conversion. There are, feet per second. So per hour, there are 3,600 seconds in an hour, so it's only going to go 1/3600th of the distance it would go in an hour. However, that's miles. There are 5,280 feet in a mile. So if we take 50 and multiply it by 5280 and divide it by 3,600, we know that the initial velocity was 73.3 repeating feet per second. So that'll get us in the right playing field. So units can be an issue, but just remember that the acceleration that we're given is in feet per second squared if it's either 32 feet per second squared or 9.8 meters per second squared. And this is all info that should be given. This is not physics where you need to learn these things. This is calc where you need to be able to work with these equations. So A of t is negative 32 feet per second per second. V of t is negative 32t plus the initial velocity. The constant here is the initial velocity. And I'm not dropping something in this case. As soon as Benny lets go of the ball, it has velocity of 33.3 repeating feet per second. So S of t is going to be negative 16t squared, as we learned on the last example, plus 73.3 repeating t plus initial height, and that's 5. Now, the question is, how long is it going to take for the ball to hit the ground? And we're looking to see if it's somewhere close to 5 seconds. All right, so again, when the ball hits the ground, its height or its position has become 0. So I'm just going to solve this equation. All right, and this should be an equation you know how to solve at this point. It's a quadratic equation. It's not going to factor. You know, we don't have pretty enough numbers that are going to factor, so we're going to have to solve it with the quadratic formula, or graph it and see where it equals 0. So I'm going to pause a minute, let you quadratic formula that, or put it in your calculator for practice. We'll come back with the t value or values when this thing hits the ground. All right, so hopefully you tried that, and we see t equals, when I solve this quadratic equation, I get negative 0.067 seconds, and I get 4.651 seconds. So first of all, why do we get two answers? So this is a parabola. It's squared. If you were to graph it, it would look something like this, where negative 0.67 is here and 4.65 is here. Now this is not a picture of the motion. Remember, this is time. This is not standing to the side and watching this ball travel through the air, because this ball actually goes straight up and straight back down. But if you graphed its height over time, these are the two times when the height was 0. So this one actually is not part of the motion. This is like if you could back the motion up from the time that the ball left Benny's hand, and this parabola is only valid. The domain only counts starting at 0. But this is like what happened before he let go of it. Sort of. It didn't really happen, but if you backtrack, that's why we get one negative answer. So this ball is going to land on the ground 4.651 seconds after he lets go of it. So the urban legend, it's pretty close. If he throws it 50 miles an hour, we change that to feet per second, we realize it takes 4.65 seconds. So not dead on, but it's pretty good. That's pretty good. I'm actually amazed it's that close from that boyhood rumor that I heard. So you need to be able to work with position, velocity, acceleration. Remember, we're integrating now, and you've got initial velocities and initial positions that make up those C values. And some other facts about motion, and it's a whole new set of problems that you can do.